Good evening and welcome. On behalf of the Energy Society at LSE, it's my pleasure to host tonight's lecture with Professor Stephenson and Dr. Baka. Before we begin, I would like to use this opportunity to promote the G3 Energy Conference that we've been organizing with our friends from Imperial and UCL. It's going to be on the 19th of March here at LSE, and throughout the day we're going to be holding a variety of lectures and panel discussions on various themes that are related to our topic, moving towards a low-carbon future. So in case you're interested, please check out the website. It's g3energysummit.org, where you'll be able to find more information as well as buy tickets. We'll also be having a panel discussion where we look at some drawbacks and benefits of drilling for shale gas in the UK, and Professor Stephenson is happy to be on the panel again. Last note, this lecture should be recorded if technology doesn't fail. So we hope to make it available as a podcast afterwards. And that's it on my part. So I would like to pass it on to Dr. Baka, who's our chair for this evening. Thank you.
Thank you, Simon, and thank you to the Energy Society for asking me to chair such an exciting event. I'm Dr. Jennifer Baka. I'm an assistant professor of geography and environment here at the LSE, and I conduct interdisciplinary research on energy policy. Worked for about 10 years on biofuel policy in India, but shale gas is just too interesting for me to avoid, and I happen to be from the shale gas regions of Pennsylvania, so I am transitioning to learn a bit more about shale gas. So it's really my pleasure to be here tonight and learn more about the scientific evidence base. So it's my pleasure to introduce tonight's speaker, Professor Stephenson. He's currently the Director of Science and Technology at the British Geological Survey, and he's held this post since 2013. And in this post, he manages over 500 scientists here in the UK. And tonight, he's going to help us shed some light on the controversies surrounding shale gas. He's going to take us through some of the scientific evidence that can help us inform the debate. So it'll be a very engaging evening, and I'm very much looking forward to it myself. So he's going to speak for about 60 minutes, after which we'll have about 20 minutes for Q&A. So with that, I turn it over to you, Professor Stevens. Thank you. Stephenson.
Thanks very much.
There we go. There we go. Let's start you off. Yes. There we go.
Thank you. Thanks very much, and glad to see so many people here. I hope it will be an interesting talk. I don't think I'll last an hour, but I'll try. How many, just out of interest, how many economists are there here? Hands up, please. Oh dear. Right. How many scientists, and I don't mean to insult the economists, but how many natural scientists are here? Oh dear. And how many geologists? Oh, right. Okay, so this is quite a sciencey talk. I make no apology for that, because I think it is a crux of the matter, the science, because I think we have to understand the science and try to get away from all the other stuff that you see elsewhere. So this is quite a sciencey talk. I'll try and make it accessible to people who aren't sort of geologists. And please stop me if you think I'm talking gibberish. But I'll talk for about 45 minutes, I think, 50 minutes. So that's the title of the talk. What the theme of the talk a little bit is to do with how science can help us to see where the facts are and where the non-facts are. So trying to understand, to use science in order to distinguish between what is not true and what is true, and what will help us to understand shale gas and what won't. So I think you'll see that as the talk develops. But I thought I'd just go through a few interesting facts, first of all, in the shale gas world. This is a slightly old fact, it's a little bit out of date, but what it essentially shows is a really startling change in American domestic gas. And what it shows, you can see, is the different colours. This was published in Nature in 2011. What it shows is time from 1990 projected to 2035, the projection from 2009, but in fact that projection is quite accurate even now in 2015. But essentially what it shows is a green, at the top, that green wedge appearing. That green wedge appeared from virtually nowhere, and that green wedge is shale gas. And there are people who predict that shale gas might be supplying, a half of the United States' gas by 2035. And that's not a fact, but certainly the growth in shale gas, certainly since about 2006, is a fact. It's really a startling fact, which is, I think, probably changed the world to some extent. Here's something which is more difficult. So I put fact question mark. So this is an image from a great film called Gasland the Movie, which shows people lighting domestic water from their taps or their faucets. And this photograph is quite easy to get on the web, and you can see it. And some people will say, and you can read things on the internet, or you can read magazine articles or whatever, that says this methane, this natural gas that person is lighting, is from fracking. It's in that water because of fracking. But you can also read in other parts of the literature, or if you read on the internet, or you can look at newspapers which will say it's natural methane. It's there anyway. And it's quite hard to tell which is true. Certainly if you just read the stuff that you see on the internet, or if you read stuff in magazines and things. Here's another fact question mark. So this is quite a famous picture, not quite as famous as that earlier picture, but it's a picture of a road in Blackpool running up to a bridge. Blackpool's, if you are not British, is a smallish town, well, largest town, in fact, in the northwest of England, where a few years ago a test hydraulic fracturing operation was conducted. And I think it was on a Friday evening, and the next morning some people claimed that the cracks on this bridge, you can see in the tarmac, were caused by fracking. And so a lot of people claimed that. But some other people said, no, they were already there. In fact, some people said there was moss growing in them, and they'd been there since the 1970s. So it's quite difficult to tell, whether that was genuine or not. It's another fairly simple question to answer, you would think. Here's another one, which is a bit more subtle and a bit more difficult. So this is from the United States. So one of the claims made by pro-gas, shale gas people, is that between 2006 and 2011, CO2 from fossil fuels declined by about 8% because of the substitution of shale gas for coal in power stations. So in other words, because more gas was being burnt than coal, the United States had a lower greenhouse gas emissions footprint. So greenhouse gas as opposed to CO2. But there are other people that say, well, in fact, there were more greenhouse gas emissions because shale gas is associated with something called fugitive methane emissions, which I'll talk about a little bit later on. In other words, that a natural problem with shale gas drilling is that a lot of methane or natural gas leaks out of the top of the well or from other places, and that all that shale gas that was being produced actually produced a load of methane, and so therefore this claim that greenhouse gas emissions were less over that period might not be true, because you might be producing a lot of methane, even though you're producing less CO2 from burning coal. So that's a difficult one. I've got a question mark. But what I'm going to try and do in the latter part of the talk is unpick some of these, so you can have a look at what the science says, what the peer-reviewed science says. So what I like to do is essentially pick apart shale gas into a set of what I call contestable areas. And I published a book last year, and this is very much my approach with the book, which was to take shale gas, divide it into chunks, and try to look at those chunks and see what the science says about each part. So here are two famous ones, two obvious questions which I've just sort of covered. Do shale gas wells contaminate groundwater? Is shale gas lower carbon than coal? And those are two interesting questions that we might want to solve. But there are loads of others. Does fracking cause dangerous earthquakes? Does fracking produce dangerous radioactivity? Does shale gas cause subsidence? Does shale gas use too much water? And there are lots of these. It's not just two. You could probably get 10 or 20 of these. But they're all actually quite tractable. In other words, we can pull them apart because there is science and research being done that looks at some of these. So some of my talk will be concentrating on some of this science. And I'm going to look at those two questions in yellow in particular. just to see what the science says. So you've probably guessed that my approach here is really to use science, to use scientific papers particularly, to attack this problem. Now, what I try to do is concentrate on peer-reviewed scientific papers. And I know I'm sitting in a room full of people who are academics and who probably know all about this, but essentially a peer-reviewed paper is a scientific paper or a paper in any other form of scholarship which is anonymously checked and read and commented on by your peers. So in other words, other scientists of similar repute will look at your stuff and say whether they think it's okay or not. And they'll do it anonymously, so they can say horrible things about you, and they do. And lots of people in your audience probably have scars of that process. But it is a good process because essentially it's a way of making sure that science papers are good, that they are independent, that they are and that they hold up to at least some sort of scrutiny. I'm not saying that they are perfect, no one believes that, but they are probably the best that we've got at the moment. Peer-reviewed science papers. It's a bit like democracy. It's not perfect, but it's perhaps the best that we can get at the moment. So what I'm going to do is show you how science papers can be brought to bear, peer-reviewed papers can be brought to bear to some of these questions. And I call it the science gauge. So it's a way of saying whether something's true or false by looking at what the published peer-reviewed science says. So I won't be talking about things that haven't been researched and haven't been peer-reviewed. The papers I will talk about necessarily are selected because I can't talk about everything and I can't talk about every area. So I will use the papers that I think are the most important. I'll try to explain what they say. But before I do that, because it's quite involved if you're not a geologist, I thought I'd go through a few simple shale and fracking basics. So I apologize for those of you who know all this, but this will help you to understand what the papers, the peer-reviewed papers that I talk about, say. This really is basic. So shale, that's what it looks like. It's very, very dull-looking stuff. And if you're a geologist, you know, it's about the last rock that you sort of turn your interest to. And in fact, you know, if you'd have gone 20 years ago, 30 years ago, you'd be hard-pressed to find a shale geologist because it's such boring stuff. But in fact, now everybody's jumping on the bandwagon, and suddenly lots of geologists are shale geologists for obvious reasons. But it is quite dull. It's sort of greyish, fine-grained, it's soft. It's very common. And this is one of the interesting things, that people think it's some kind of terrible, frightening rock that will kind of bite you if you're not looking. But in fact, shale is very, very common. 70% of the world's surface rocks are sedimentary, and 50% of those are shale. And if you are interested in walking in the Peak District in for example, the north of England, then a lot of the time where you're walking around, you're walking on shale. It's not rare at all. It's all over the place. There's tons of it here under London as well, and under Hampshire, and out under the central parts of England. What's interesting about shale is it contains a lot of organic matter, which is basically a sort of organic mush. Up to 10% of it by weight is organic matter, which makes it quite unusual. And if you take a lump of that shale and dissolve it in a very strong acid, like hydrofluoric acid, you can extract only that organic matter. And that's what it looks like. That's a very highly magnified image, but essentially you're looking at an image about 0.5 millimeter across of what the organic matter in shale looks like. And it's quite interesting, well, to me it is, probably not very interesting to lots of people, but it contains elongated fragments, which are probably fragments of wood. That long thing there is a fragment of wood, an ancient piece of wood from a forest, probably about 330 million years old. This little thing here is a tree spore. And here's another one, a spore of a tree that doesn't actually exist anymore, an extinct, a huge tree which grew at about 10 meters a year, but which probably contributed a lot of the organic matter that sits in shale. So the shale in the north of England that I'm particularly going to be talking about, the organic matter that makes the gas, because this is why it's important, that makes the gas, came from ancient plants mostly. There's nothing weird about it, it's simply ancient plants. So this is what the organic matter might have looked like. And you can see here a sort of pretend coastal plain with some trees growing on. Imagine you're back 330 million years ago. So you're way, way back, way before the dinosaurs, way before even advanced tetrapods and things. You're really way back in time. And you've got some very primitive plants growing on the land, and they're dropping plant material into lakes and into the sea, and that mud is collecting. And the mud contains all this mush, that's not a technical term, from all the woods and the trees around. And that is the organic matter that is in the shale. And the mud, essentially, is the shale. So mud just turns into shale when it gets compressed and when it gets heated up. Shale is just mud, really, that's been cooked up and it's been compressed. It's hard, a hard version of itself. So that's what it looks like, and that's really where shale comes from and the organic matter. But if we imagine that mud collecting, and there you are at the top of up there, you can see that landscape there with the mud collecting in red, and you've got lots of layers of rock underneath. As time goes by, because more sand and mud is coming in, because all the time sand is collecting, the mud goes down because it's being buried by later sediment. It's really a very simple concept in geology that rocks higher up are younger than rocks lower down. And so you see the mud is now, 20, 30 meters below the surface. And at a certain point, perhaps at 2 or 3 kilometers depth, so after a really long time, maybe 10, 20, 30 million years, when the shale has got down much lower like this, because all the stuff is on the top, you've essentially turned to shale. The mud has turned to shale. And when it does that, it actually turns to gas as well. So the organic matter in the shale gets cooked up into methane. It's a pretty simple process. None of it's complicated. And there's 2 other things that you should know, simple things that you should know to understand the rest. And that is shale looks rather like that if you have a powerful microscope. It's lots of squashed particles all crushed together. And the gas in it looks like that. It's completely, inside these tiny particles. It's very, very sort of mixed up with these tiny particles. What that means is it's quite hard to get the gas out because the stuff is so squashed and so squeezed that the gas doesn't move very easily between the particles. A sandstone looks like this if you have a powerful microscope. And if you look at the gas in it, that's gas. You can see really easily that gas moves around easily in a sandstone. So when you drill a hole into sandstone, if you're an oil and gas person, the gas flows out very easily. And that's called conventional oil and gas because it's easy. It's conventional. They're used to doing it that way. And this, because the gas doesn't flow, if you drill a hole into shale, gas doesn't really come out very much. It's called unconventional. I remember looking up unconventional on a Schlumberger website, and it said gas produced in non-conventional ways. Not very helpful. But essentially, unconventional means, it's not what we're used to. So unconventional is gas like that in shale, and that's important for the later parts of the discussion. Another very simple thing, what is fracking, or hydraulic fracturing? Well, it's about drilling a hole, and this is very, very exaggerated in scale. So you've got to imagine this hole is much, much deeper. I couldn't really represent it on a proper slide because the hole would be going way, way down there to the floor below us. But essentially, when you drill a hole into a shale layer, then you drill a horizontal from it in order to follow the shale layer. And what you essentially do, in order to get the gas out, and remember the gas is suffused inside the shale layer. It's amongst these tiny, tiny particles, very hard to get out. In order to get it out, you have to crack it. And that's what hydraulic fracturing is. You essentially pump a fluid down the well, very high pressures. It's able to find its way into the hole, and because it can't do anything else, it cracks open the shale, and it moves into the shale. And because it does that, when it's taken back out again, the gas flows into the well. So hydraulic fracturing is pretty simple. In order to keep cracks open, sand is pumped in. So the sand grains go in and hold the cracks open. And that's why they pump sand in, so that the cracks stay open so the gas flows out. So it's fairly simple. So that's what hydraulic fracturing is. Yeah. If you don't mind, maybe I could ask the question at the end, because there's a pile of slides to get through. Yeah. Okay, I can answer the question at the end, but I think if I could just sort of keep on to this, because this is the basics. Yeah. So this is what it might look like. So, well, not what it might look, this is what it does look like. So this is a fracking site in Alberta that I went to not long ago. What you notice is it's quite a small area, about the size of a football field. This was in northern Alberta. There's sort of woods all around, very, very open landscape. But then you get these tiny areas of intense activity where there's trucks and pipes, an enormous amount of noise, absolutely a skull-battering noise, as I say in my book. And that's what I remember about the place. It was just an amazingly noisy place. And these big frack trucks are parked around. These are the things that deliver the power, that generate the power that produces that high-pressure water that goes down the well. And these frack trucks are often lined up, a whole group together, and enough power to deliver that enormous pressure in order for the frack to happen. It may happen 2 or 3 kilometres below the surface. These are tanks which hold the flowback. So the flowback is the frack fluid that comes back out of the well after you've done the fracking. So the water's going into these fracks and it pours back out again, and they collect it, and they usually use it again. So that's what flowback tanks look like. Just showing you what the pictures what it looks like. This is a truck carrying proppant. So proppant is the sand that you pump into these cracks to hold the cracks open. And, it's a great place if you like big trucks, because, fracking sites have a lot of big trucks, and lots of trucks going in and out, carrying things in and carrying things out. Okay, so I was asked by the LSE when I agreed to do this talk to have something about how much shale gas is in the UK. So this is a slight diversion from the normal course of the talk. I am going to come back to those 2 questions about the low carbon aspect of shale and the groundwater contamination. But for a second, I'm just going to go off into the shale gas in the UK debate, because I sense as economists here, you want to know what the resource is, because, if there's no resource, there's no point in talking about it. But if there is, how big is it, and what does that mean for the United Kingdom? So the BGS, we are the Institute for the Study of Geology in the UK. We're a national institution. We are government. And so we do this kind of big survey. And we did 3 big surveys for the UK to have a look at what we thought the resource of gas might be in the country. So up in northern England, we looked at this area, which is quite an important area. We think this is the most prospective area. So it's around sort of Lancaster in the north, Nottingham, Manchester, Liverpool, Leeds, Sheffield. We also looked down here, Jurassic Wheel Basin, south of London, and also the central lowlands of Scotland. Those were the 3 areas we chose because we thought those were the most important areas. And essentially, what we did was a big geological study. It took quite a long time. It's all peer-reviewed. It's all in the public domain, so you can see exactly how we did it. But essentially, what we did, and I don't want to go into too much detail, is this is a map of the northern England part that I mentioned earlier on. This is the edge of the area we studied in purple. Those blue lines, those thousands of little blue lines, are seismic lines. So they are essentially cross-sections of the geology, the soundings, if you like. So you use very loud noises in order to understand what the subsurface structure of the rock is. The black dots are boreholes, and the yellow colour is the outcrop of shale. So that's where you can actually go and see it actually in the hills. So we use that kind of information and that data to come up with some answers. So for the north of England, we came up with 1,300 trillion cubic feet of gas. And that is, it's very important to understand. It's a resource figure. not a reserve figure. I'm sure economists here will understand that completely, but if you're not familiar with it, essentially the resource is what we think is under the ground. Fairly simple. The reserve is something much more complex and sophisticated. The reserve is what you think you can get out of the ground under social, economic, and other conditions, under those limitations. And so typically, the reserve is many, many times smaller than the resource. It could be 1% of the resource. It could be 10% of the resource. So it's a very different concept. But in the north of England, we've got quite a lot of gas in terms of resource, 1,300 trillion cubic feet. It's in two layers, the green and the orange layers. That's not actually where they are, it's underneath that part of England. So you can see places like Manchester, Sheffield, Derby, Liverpool, Blackpool, up near Leeds. These are all areas where you've got what appears to be quite a lot of shale gas. This diagram you can easily get on the web. What's interesting, and as a geologist, and I'm sure many people in the audience immediately see, a lot of this gas is sitting under big cities in the UK. And that's really, therein lies the biggest problem for shale gas. If there's anything that you take away from this talk, and I'm probably talk for another 30 minutes, you could probably ignore what I say for the next 30 minutes. That's the problem, is that you've got a lot of people living on top of a lot of all that shale. And the reason for that really is quite interesting. It's a historical situation, really. A lot of those towns are industrial revolution towns, where Britain began the Industrial Revolution, and that was mostly powered by coal. And the coal is related to the shale. The shale sits under the coal, and it's a similar age, and it's similar stuff. So in fact, all we're seeing is the same thing over again. So you've got the big industrial cities of the UK sitting on top of coal that was burnt, that made these cities rich, and now here's shale, and shale's underneath this quite densely populated area. This is what we thought about the central lowlands of Scotland. We don't think there's much gas there, but we think there's 6 billion barrels of shale oil. That's not really very much, on the scale of things, particularly not so the United States resources. For London, for southeast England, we came at 4.4 billion barrels. Again, not very much. This is quite separate from the oil that's been recently discovered near Gatwick, the so-called Gatwick gusher, which was talked about on the news last week. That's not shale oil. But this is what we think about shale oil in the south of England. So not really very big. The only big one is that one, really, is the north of England, in our opinion. So that was a little diversion off into British shale gas, for those of you who are interested. I'm happy to discuss that later on. But I think I'd like to get into the meat of two questions here, which I think are interesting. And those two questions, I think, are important because I think lots of people gather around them as problems in shale gas. I can't do all of those difficult contestable issues, but I'm going to try and do two. So I think this is the most important and interesting one for the UK, I think, at the moment. Do shale gas wells contaminate groundwater? Okay, so we're going to have a look at some peer-reviewed papers, some peer-reviewed literature. But first of all, we need a little bit of basics again, just so that you understand what the papers are saying. So the first thing to realise is that there are a couple of types of underground methane, of underground natural gas. There is biogenic methane, which is an obvious origin. It's caused by bugs, by living things. And it tends to be close to the surface, not always, but you can find biogenic methane in rocks and in sand. It's not in big gaps or holes or caves. It's just amongst the particles. And it's being generated by bugs, essentially, by bacteria. But there's also thermogenic methane, and that's the methane which we associate with shale. And it's caused by heat. If you remember my diagram showing the shale being buried and being cooked and heated as it gets buried, that's thermogenic methane. So one way of telling between two different kinds of, it would be very useful to be able to tell between these two different kinds of methane. And, remembering that photograph of the guy lighting the tap in a Pennsylvania kitchen, it would be interesting to know whether it's biogenic methane or thermogenic methane. Because if it was biogenic, it would be less likely to have been caused by fracking. If it was thermogenic, then it's more likely to be caused by fracking. So, sorry? Oh, well, well, let's look through the papers and see what it says, okay? Let's just look through the papers. So how do you tell between biogenic and thermogenic? Right, so thermogenic methane, I mean, this is a sort of geochemical diagram, but it's easy to understand in the sense that all you're doing is you do a scatter graph like this. You have a certain ratio here of different kinds of gases, and essentially an isotope ratio of carbon atoms carbon isotopes in the methane. It's quite technical, but if you do this, you can plot different kinds of methane on a diagram like this. So biogenic and thermogenic methane can be distinguished. That's useful because you should therefore be able to tell something about the origin of the methane. It's not always as simple as that, as we'll see in a minute. But it is important to realize that geologically, you can tell the difference between these different types of methane. And I'm going to talk about Pennsylvania particularly. And unfortunately for the people of Pennsylvania, it's turned into a bit of a natural laboratory for shale gas researchers and scientists, because it's really a place where a lot of shale gas is being drilled and a lot of research is being done. So almost all the research that I will talk about in the next 10 minutes comes from Pennsylvania. And it comes from the drilling of this famous shale called the Marcellus Shale, which is one of the biggest shales in the United States. It underlies an enormous area of northeastern US, including Virginia, you can see Kentucky, up into New York, in New York State. So it's a massive area which is underlain by this shale. And you can see on the left, those dots, the red and the green dots are wells that have been drilled. I'm not sure if that's the wells drilled in the last few years or the total wells drilled, but you can see the density of drilling. An enormous amount of drilling has been done in Pennsylvania, and it's a great place to study shale and shale gas if you're interested in questions like contamination of groundwater. So those are the basics. Let's look at the first paper. So this is a great paper, well, it was thought of to be a great paper at the time, published in 2011 by Osborne et al. It was by the Duke University Group. And if you're interested in these papers, I can also send you the links to them. But it was published in a very famous journal, Proceedings of the National Academy of Sciences, one of the most august journals in the United States. It's peer-reviewed, it's very carefully peer-reviewed, and it caused an absolute storm because it was really the first paper that went out and said, shale gas fracking is contaminating groundwater in Pennsylvania. It says so in the abstract. It's absolutely unequivocal. So what did they do to come to this conclusion? Well, they measured the methane content in the wells, water wells, near to the fracking wells. They measured the delta 13C, which is this isotope ratio that helps you distinguish between biogenic and thermogenic methane. So they measured that as well. They noticed higher methane concentrations in water wells close to shale gas wells. That was interesting. So they were immediately thinking, well, if you're getting higher concentrations of gas close to wells, that must mean something. They also found that the delta 13C was thermogenic. So they immediately said, likely to be shale gas from the fracking. So that was an interesting thing. Obviously, the industry hated it because it cast doubt on their ability to keep to keep the thing in control. And it was very interesting for lots of other people. So the paper is enormously well cited. So again, academics in the audience will know the importance of your papers being cited. This was cited hundreds and hundreds of times. So the Hirsch indexes of these people have rocketed through the sky. You know, scientists sometimes know what to study because they pick the right things. Another paper came along about a year later. This is a paper in Groundwater, not such a famous journal, but again peer-reviewed by Malofsky et al. It's an interesting paper. And what they looked at is some of Osborne's data. So they looked at some of the data of that previous paper. They also commented on things that Osborne hadn't said. For example, there's quite a long section about how historical records in Pennsylvania show that flammable and effervescing natural springs were present. And there were water wells with gas coming out, naturally. And these were recorded back into the late 1700s. Hundreds of years of folk knowledge of gas pouring out of streams and out of areas, natural gas, and lighting it as well, being able to light it. So they made that interesting point that there's quite a lot of methane in natural water wells in Pennsylvania. And they showed this map, which I think is a great map, which really, even if you're not a geologist, it's quite quick and easy to see what it seems to be suggesting. First of all, this is an area of Susquehanna County in northern Pennsylvania, probably the most densely drilled area. And those red dots are water wells. There are lots of water wells in northern Pennsylvania. And those water wells had methane amounts measured in them. And the ones which have the big red circles have a lot of methane in them. The ones with small red circles have a small amount of methane in them. What's interesting is that some of these, well, first of all, the fracking isn't the whole of this area. It's a small part of the area. So, first of all, the biggest conclusion you can draw is there's a lot of methane in Pennsylvania water wells. Whether you're near fracking areas or not, naturally. The second thing is, there's a lot of methane, and I think everybody can see this, along valleys. If you look, the river valleys have water wells with more methane in. And that's very interesting geologically, because river valleys tend to follow faults, geological faults or cracks in the earth. So immediately, as a geologist, you look at that and think, is that methane coming up natural faults? And is that the reason why it's concentrated in some water wells? So that was a very interesting paper. And what it tended to do is look at Osborne and say, well, Osborne might be right, but there's an awful lot of natural methane in water wells. And this is one of the most interesting diagrams that was published. And what it showed was a cross plot that I showed you earlier on, which you used to try to distinguish between thermogenic and biogenic methane, that cross plot that I illustrated earlier on. And they took Osborne's data and they plotted it onto the graph. And where it plotted was very interesting. It plotted into that oval shape there. The black triangles are Osborne's data. And what you notice is that it doesn't plot in isotopic terms in the Marcellus shale area. This is the Marcellus down here. What this cross plot seems to be saying is the gas is coming from layers above the Marcellus. So they thought that must mean that there is gas getting into these wells, in water wells, but maybe it's not coming from the fracking, it's coming from something else, causing leakage higher up in the rocks. So it's a very interesting sort of detective story. I'll come back to it. Now, this group from from Duke University, well, kind of by this time they were smarting and pretty angry because they'd had quite a lot of criticism of the paper, mainly because their data wasn't very big. It wasn't a big data set. So they came back again. This time they stuck Osborne down the list of authors, and they stuck Rob Jackson at the front of the author list. He's a famous geochemist from Duke University. He authored this paper. And they went back and they really attacked this time. They did a much bigger survey. So no one could accuse them of, doing too little data. So they looked at 141 water wells. And again, they found methane concentrations 6 times higher for water wells within 1 kilometre of shale gas wells. Interestingly, they didn't find a correlation with valleys, which is what the previous map seems to show. But what is interesting is that, statistically, this paper holds up. You have got a problem of leaking wells in this area, or methane. Sorry, you have got a problem of methane in water wells, near shale gas wells. Recent research, now this is really going fast now because there's so many people interested in it. You've got lots of scientists sort of piling in, looking at these interesting areas. So Llewellyn et al. Is a recent paper. This is the only paper so far which suggests that frac fluid has been found in groundwater. All the other studies have suggested essentially that the methane you're finding is completely just methane. There's nothing to do with the frac fluid. And that has tended to suggest to lots of scientists and geologists is that the problem is with the wells. It's not with the fracking. It's the wells moving up through the shale, that somehow they're leaking. But this is the only paper, to my knowledge, that suggests that there is a problem with frac fluid getting into these groundwaters. And even Llewellyn et al., if you read the paper, are very, very cautious about this because they found a frac fluid chemical in the groundwater, but they are not really sure if it's come from fracking. They sort of speculate about it, but they also say it could have come from a leaking, tanker or something like that at the surface. But that's an interesting paper. Another one is by Dara et al. Sorry if you're kind of overloaded here, but it's kind of the core of the problem, this. So Dara et al., really interesting paper, and they used a new technique harnessing noble gases, which are coming from deep in the core, naturally up through the crust. And as they move up through the crust, they collect methane and move with the methane. And there is a way, which they detail in the paper, of distinguishing between what they think is methane that's leaking from a well and methane that's leaking from fracking. And what that paper suggests essentially is the problem is about the wells. It's not fracking that's causing this gas to get into people's water supplies. It's the wells that go down to the fracked levels. There's something wrong with the wells and the way that they penetrate the rocks. This paper here is essentially the same one written again. It's a very academic trick of writing the same paper twice. They're giving it a slightly different title. But there's a bit more data in this one. But this is one of the most important set of papers because essentially it sort of clinches the deal. It sort of says, well, it's much more likely that the gas is coming out of wells rather than directly out of fracking. Of course, that doesn't mean that anybody's off the hook. This is pretty bad. This is a lot of leaking. And if you can go on the internet, I know I told you not to do, but you can go on the internet and see YouTube films of what appear to be gas leaking out of the tops of abandoned wells or of wells that have been used. What's interesting as well, and I'm nearing the end of this part, is outside of Pennsylvania, the studies so far, and I can't pretend to know everything, but the studies so far suggest there aren't any problems. So this is a paper from Arkansas where 127 drinking wells were studied by the same group using the same methods. They found, they know that this is an extremely well-developed shale area in Arkansas. They found 4,000 shale wells. They found very low concentrations of methane. They found it was biogenic. There's no leakage. It looks like it's a Pennsylvania problem. So, in conclusion, and I'll come back to this, it's clear that shale gas wells in parts of Pennsylvania appear to be leaking. Water contamination is most likely from the wells themselves, not from the fracking. That's what the science is saying, apart from the Llewellyn paper. And I think there's a question mark over that needs to be looked at. So I'll come back to these conclusions again at the end. Let's look at the next question, which is shale gas lower carbon than coal? I deliberately picked this one. Yeah, it would be better because I can... Yeah, I'm going to do that now. I'm going to do it now. I mean, that's what this one's about, this bit's about. So this bit here is about, methane emissions, about fugitive emissions. So is shale gas lower carbon than coal? Good question. Right, the reason why I asked that question is because there are people out there who are saying, let's replace coal with shale gas, or at least with gas. If we do that, then we'll limit emissions. Is that true? I've chosen a wonderful diagram from a famous paper from two Princeton geologists, Baka and Sokolow, who essentially looked at the problem of carbon dioxide and the problem of emissions, and they said, okay, we're at the moment on this terrible upward CO2 cycle. We have a terrible business as usual shape like that. What we really want is the flat path. We want not to be producing this kind of CO2 emissions. And if you look at their idea, they essentially divide that, they take that triangle and they divide it into 8 wedges. And each one of those wedges they call a carbon abatement stabilization wedge. It's a complicated name, but essentially it avoids about 1 billion tons of carbon emissions. And in that paper, which is a nice little paper to read, they essentially say this: if 1,400 natural gas power stations were substituted for an equal number of coal-fired power stations, this would be 1 wedge of CO2 emissions. So in other words, if you replace a whole load of coal power stations with gas power stations, you achieve 1 wedge. So it has a sort of scientific credibility, this idea that you could get rid of a lot of emissions simply by replacing coal power stations with gas power stations. So that's why I'm having a look at this problem, because it's an interesting one. So the chemistry surely is the simple way of doing it. Surely you just go to the chemistry. And I'm not a chemist, but you can download tables like this easily. And you can see this is the amount of CO2 emitted per million BTU of energy. Pounds of CO2, this is an American diagram, but essentially you can see coal at the top coming in at about 286 pounds of CO2 for unit amount of energy. And if you look at natural gas, it's 117. It's about a half. So the chemistry essentially tells you something very simple, that if you burn coal, you get double the amount of CO2 for the same unit of energy. And that's simply a fact. So shouldn't we go away, therefore, and think, that's right, then if we just replace coal power stations with gas power stations, we'll have half the emissions. Easy. Well, again, it's not as simple as that. And the main reason, is because methane production at shale gas wells and probably in other oil and gas areas, there are opportunities for methane to leak. And you can see here, this is a flowback tank. This is a tank which is open to the sky, where flowback, which is the water that's come out of the shale well, and it's just been dumped into this tank. And that water is full of methane. So the methane is just coming out into the atmosphere. And this was fairly common practice. It's much less common now. In fact, in the UK it wouldn't be allowed. But essentially it's a way in which methane, which is a very potent greenhouse gas, it's much more potent than CO2, can get into the atmosphere. And this is how the problem hinges, really. You may be able to produce CO2 lower in a gas power station, but if there are a lot of methane emissions associated with shale gas production, then that offsets that CO2 reduction. So we have to know, really, is this a true problem or not? Is it really a problem? So this is really the basics, if you like. So here's your shale layer, here's your well, there's the well top. So the brown arrows are essentially methane escaping. So it can escape around the well, or it can escape from this flowback tank. So that's what we mean by fugitive emissions. And you can measure these. So it shouldn't be an impossible problem to put some scientists on this to measure whether there is a lot of gas coming off or not. You would say that, wouldn't you? It's not quite as simple as that. So again, we have a series of interesting papers, which again, if you're interested, I can send you or give you the links to. This is a paper by Howarth et al., and it came out about a similar time to Osborne. And what it said was really shocking. And again, the oil industry, were pretty upset by it. They said, using direct measurements, that 3 to 8% of the total methane production escapes to the atmosphere through the lifetime of every shale gas well. So in other words, 3 to 8% of the gas down there isn't getting into the pipes. It's actually getting into the atmosphere, which is a shockingly high amount. I mean, this is an amount that's enough to really make a difference if you realize that methane is a very potent greenhouse gas. So they actually speculated in their paper that shale gas is worse than coal because of this extra methane associated with its production. So this paper was very controversial. It's interesting because the same group in Cornell, I think actually the same department, had a group that didn't agree. And I can't imagine what the senior common room was like at the time, but it was obviously they're not very happy people. But Cathles et al., who's at the same university, published a very strong rebuttal of that paper, saying that it was very unrepresentative, saying that the measurements were not representative of the shale gas business in general, because there were a small number of measurements and it was in a particular, an unusual case. And you can see a table here from a recently produced paper, report by Mackay and Stone, actually commissioned by the British government. And what it shows is a comparison of amounts of gas released during flowback for different layers. And you can see the Howarth paper up here. I put a red circle around it because it shows how high it is. And so this pair of authors said this was anomalously high. Others are much lower. So there was a sort of, depended on which camp you were in. Some people said that the Howarth paper was really a problem and there's something terrible about shale gas. Other people said no, it's unrealistically high. They haven't got it right. The paper's good, but it didn't use the right data, or the data wasn't enough. So somebody came along, Alan came along, University of Texas, and did an enormous study, essentially to try to calm everybody's nerves, to look at the problem and try and solve it. So they looked at over 190 shale gas sites all over the United States. So they tried to go to different places. And they used the best method they could, and they published it again in the Proceedings of the National Academy of Sciences. Again, it's a peer-reviewed paper. What they came out was leakage rate is about half of 1% of gas production. You can see the comparison here. This is what Alan et al. Said, and this is what Howarth said. You can see the difference. It's enormous. Much less than that 3 to 8% estimated to Howarth.
That study was sponsored by the oil and gas industry.
Yeah. Well, let me just finish. So this paper, which was peer-reviewed and published, okay, maybe there's something behind it, but it was published, okay? Now, what's interesting is that a paper very recently published, this year, in fact, I think it's quite interesting because it's almost a kind of battle between the two sides. So the author of the paper is somebody called Touche, which I quite like, Touche Howard. And Touche Howard came along and said, well, we've checked this, we've looked at the Allen paper. Again, this is a peer-reviewed paper, it's not a report, it's gone through a peer-reviewed process. They looked at the paper and they said the machine they used to measure, that Allen used to measure fugitive emissions, was overestimating. In fact, by a factor, I can't remember what it says, but a factor of 3 to 5. In other words, Allen's measurements were wrong. They were far too low. And that's where we are at the moment, really. So that this paper is sort of saying that Allen was wrong. So we're back in the sort of Howarth territory of quite high methane emissions. And there's lots of other studies out there that suggest that methane emissions are quite high, from the oil and gas business generally. So, the science, although I said peer review is really important, you can see how science doesn't actually give you a straight answer. It takes time to do it, but it's getting there. I can't really give you a conclusion on that one, though. So to finish, with the two questions I chose, going back to what I said, so do shale gas wells contaminate groundwater? They do in Pennsylvania. I don't think there's any doubt about that. It's quite a small number of cases, and it's in a particular area. Fracking doesn't seem to cause it directly, unless the Llewellyn paper is right. You might have to go back and look at that. Other areas of the USA don't seem to be affected as much. That might be a naive point to make, but that's what the science seems to be saying. Here I speculate, perhaps I shouldn't, but I think probably the reason is there's something wrong with the wells, the way that they're cemented, the way where they go through some of those layers in Pennsylvania. Maybe there's something not binding, so that there are gaps between the edge of the outside of the well and the rock itself, so the gas is coming up through that space between the two. But I don't think really anybody's tackled that yet. Is shale gas lower carbon than coal? I think the jury's out. We don't know, because, if you'd asked me 6 months ago, I'd have said it is, because of that Allen et al. Paper. But really, this more recent paper's kind of pulled the rug from under us. But I think it shows that science is important, and you have to kind of follow the science. It's no good just sort of reading the first thing you see, because it tend not to be very reliable. So, conclusions. What I try to do is show you that you can apply science in a sort of forensic way for these contestable issues. It's important to society. It's not just big telescopes, and this is my sort of lame attempt to sort of say something in support of applied science, because applied science is really important. It answers these sorts of questions. We don't look at big galaxies and things, and we don't, accelerate particles, but we do things which are important. Okay. If you're interested, the way I've tackled this problem here in this talk is very much the way I tackled it in this book. So if you're interested, I do take each of these problems and try to attack them all. If you're also interested, there's a free open access paper that I published in the same journal as Touche Howard in Energy Science and Engineering, which you can just download off the web, which is, I think, a reasonably good summary of the situation is at the moment. That's it. I think there's someone who wants to ask a question. So.
Well, we have a microphone. Okay, that our host will circulate. So if you can just ask your question in the microphone, because we are recording. So we'd just like to capture it for the future distribution. So if I can just have a show of hands of questions. We have about a half hour. So maybe we can start in the back and work our way forward.
Hi, the Milsafaika, former LSE alumni, currently in asset management. I'd like to know is about the amount of shale gas in the UK. How much is that is actually recoverable, and is that even possible with the technology we have now to do it?
Okay, a good question. And I think I'd refer you back to that map that I showed you with all those big cities sitting on top of the gas. And I think that's the issue here in the UK. If you look at shale in the United States, it underlies big open areas where there aren't many people. Here in the UK, it doesn't. So, it's never going to be a high proportion of the resource that I mentioned. And really, it's disingenuous to talk about the UK having enormous resources of gas, because inevitably we're not going to be able to take large amounts out, because, we're a crowded island. Even if, everything goes as the shale gas companies want it to go, I honestly don't think they'll be extracting very much. But, if you go to somewhere like the United States, you may get a 10% recovery factor, which is 10% of the resource. 10% of the resources reserve. That's really impossible to say in this country. It's absolutely impossible. And it would be very irresponsible to quote a figure. It could be 0%. It could be 1, it could be 2, it could be 3, it could be 5. So I would certainly say it's going to be low.
Was there a question back over here? That I saw here. Yes, please.
Hello. George Rashka. So the government's kind of over-inflated kind of hype on what fracked oil and gas is going to deliver, is that just based on ideology?
Well, I'm a humble geologist. I'm not going to answer political questions. I mean, I think at the core of it is that resource reserve thing. And if you do hear politicians saying, well, you've got an enormous amount of gas, it's Abu Dhabi all over again, that's not true. But, we really don't know what proportion of the resource could be turned into reserve. We really don't know.
Right here, please. Maybe a microphone.
What's the mechanism by which the radiation or radioactivity can be released, and is there in fact any truth in that allegation?
Okay. No, shale is weakly radioactive. It's very interesting. In the British Geological Survey, we store a lot of shale. And you can, if you're going with a Geiger counter, you can tell it's slightly more radioactive than your average rock. It's not as radioactive as granite, for example. So if you're in somewhere like Aberdeen, there's quite a lot of radioactivity. Same in parts of the southwest of England. Shale, in parts of the north of England, it's not much above background. It's quite low. But the point is that radioactivity can get out because essentially you're pumping water down into a shale layer, and then the water is bringing back stuff that it's collected. So things like radon, radioactive gas can come out. But it is interesting that that is a problem of all conventional gas. And many oil fields around the world and gas fields around the world that produce gas conventionally have to deal with the radon problem, in the sense that it's there, it decays and it produces something which is solid, and what that means is that the inside of pipes that carry gas contain this quite highly radioactive scale, which has to be removed, and then it has to be disposed of in a particular way. So it is a problem, but it is a problem that the oil and gas industry knows about and knows how to deal with.
Is it a problem with the domestic consumer cooking gas in their kitchen?
I see. Well, I don't know if there's any more. The radon decays very quickly for a start, and you can't put radon into the gas pipeline. It's not allowed. And again, that's something that the oil and gas industry understands very well. So it wouldn't get into your gas supplies. But I'm not saying it's not a problem in the sense that there is radioactivity associated with shale. That's absolutely true. Not much, but there is.
If we can come to the back here, woman in the white sweater.
I've read a report where a town in Holland, where they've had a long-established shale gas extraction site, which has been running and managed well for many years, but they're getting increasing number of tremors, damaging many years, and after many years, the government are actually acknowledging that.
Yeah, that's gas. That's a conventional gas field. It's Groningen. So it's in the north of Holland, and what they essentially have been doing over many years is extracting gas out of a sandstone. Do you remember the picture I showed you earlier on, which has these larger particles where the gas flows very easily? They've been taking gas out of that for a very long time. And when you do that, it alters the sort of mechanical character of the rock. And what has been happening is it has been kind of moving, and there have been earthquakes. Yeah.
Is it on? Yeah, cool. A couple of comments and then a question. In Britain, we've actually been using fracking for several years. It just happens to have been in offshore wells.
Yeah.
The science is relatively well known, and we use it to get oil and gas out of tighter. They just happen to be offshore. You raised a good point on the flowback, so the gathered water, and then mentioned that would likely be illegal if it were to be replicated here. And personally, I think that's a way forward, is to actually have careful regulation with proper penalties. Do you see other areas of the shale gas, so-called production or flow chain, that could be better regulated if, say, compared to Pennsylvania? Personally, I think this is at least a way forward to find out what we have and whether it's economic. But
Okay,
we need
I'm
proper
not an expert in
regulation.
You've got to be careful what you say, because I don't want to give you what's not right. But I was with EA people this morning, Environment Agency, and if you do transgress environmental regulations in this country, you go to jail. And if that means that shale gas companies don't do the right thing, then the Environment Agency, I don't know if it's the EA, but we have the teeth to be able to put people behind bars if they don't do it right. But you're right. I mean, situations like open flowback tanks are clearly not acceptable. And similarly, things like water disposal. So we know that, for example, in the United States, a lot of water that comes back from fracking or produced water is injected, because you're in arid places far away from the sea, and there's nothing you can do with this relatively dirty water. So they pump it into the ground, it causes earthquakes, and it's obviously causing quite big earthquakes. But again, I think in this country, it's extremely unlikely that, well, you would need to do that because we are not a huge arid country, and we have the facilities to be able to process and to clean up water. And it's a normal industrial process to have to clean up water from factories and installations. But I think there is, but to answer your question, I think it's not an issue of that. It's an issue of regulations manifestly protecting people. And people obviously don't believe that they do at the moment. And that's a challenge for the regulators.
Is that behind you in the green shirt?
I think we should let the lady speak.
Thank you very much. Very good presentation, sir. I'd like to understand a little bit about the costs involved. Now that the price of oil has come down to $30 and solar energy, the progress because of technology, the costs are coming down a lot. Is there a lot of scope in cost reduction in shale? And is shale more capital intensive or less capital intensive, means as opposed to operational cost versus capital cost?
I suspect there are many people who can answer that much better than me in the audience, as economists. But essentially, what's been happening, an enormous amount of production of oil. I don't know if this is true, but to try and drive shale in the United States out of business. And, the price of gas has dropped and dropped and dropped. But they're still there. Maybe not so much in Pennsylvania, but they're still doing it. And they have reduced costs. And I read The Economist. I've got a sub to The Economist. The Economist thinks that the shale gas industry is incredibly resilient because it's just managed to survive, even under these incredibly pressing circumstances. But I suspect it probably can't adapt much more. But it's clearly resilient, yeah.
The two main reasons the prices of shale is remaining resilient is one is that they've managed to go further and longer with the wells they're drilling, i.e. they're getting more distance and more production out of a single well, which means instead of drilling 6, you drill 2, for example. And the other one is when diesel and oil fall, so does your cost of shale drilling because diesel is your biggest input fuel into drilling. And you apply those two and you get a natural decline in your operating costs at the well.
We come to the front. We'll just get the microphone for you.
Can you tell us about the peer-reviewed studies that cover what to do with returned frac fluid, whether injecting or treating or mixing it with sewage and dumping it at sea? It seems to me that there is no way worldwide of doing that satisfactorily, and that in the UK, the UK Water has said that no company is willing or able at the moment to take even the amount of returned frac fluid that would come from the wells that are being disputed at the moment in Lancashire.
Well, I think, industry in this country produces a lot of dirty water. Steelworks, not many of those left, but they produce a lot of dirty water. Everything does this, and we're quite used to dealing with it. Industrial processes produce water which we can clean and return to watercourses. We've been doing it for a very long time. If your question is a very large shale gas industry producing an awful lot of produced water and returned frac fluid, would that be a problem? Yes, it would, and it's a problem in the United States where clearly they've had to resort to injecting wastewater in deep rock formations, and that has been causing earthquakes. So there is peer-reviewed evidence that has happened, but that's an aspect of the oil and gas industry, which they probably have to sort out. Yes, that's right. Yeah. But I don't. The Environment Agency have said here that it wouldn't do that here because we've got the ability to process water. I can't comment on that. I don't know.
Thank you very much for the talk. It was incredibly informing. My question is concerning, do you know of any other studies in the US, other than the one in Arkansas, of an appropriately large sample size to yield a statistically significant result to either corroborate or to impugn the idea that Pennsylvania is
Very good
an
question.
isolated instance of contaminated water supplies near fracking wells?
Very good question. I don't. And that may be because I haven't been reading the papers as carefully in the last 6 months as I did before when I wrote my book. So I read everything I could. And there may be incidences since then of peer-reviewed papers showing leakage. Not to my knowledge, not. Because they tend to, if they do, they tend to get in the news. And very quickly. And you tend to know. To my knowledge, not, but I may be wrong.
Other questions? Can I come here, please? And then we'll come over.
Thank you. Just want to clarify. So the first question that you looked at, which is whether fracking itself causes water contamination. So you suggested that the paper seems to point to the consensus that it's the well itself, not the fracking.
Yeah.
From my complete layman knowledge, understanding, isn't that during the well that's part of the unconventional fracking process? How do you separate?
Maybe I did sort of go over that quite quickly, but essentially the reason why people think in general that fracking is not the result of this high methane in water wells. You can't dispute that, that's true. But the reason why, there are a couple of reasons. One is that until very recently, no frac fluid was found in this methane that was present in the water wells. So in other words, you would think as a geologist that if there was contamination, the frac fluid would be amongst the gas. But they didn't find that, except for this Llewellyn paper. The second one was that Molofsky data that I showed you, which showed you that the isotopic value of the methane was not that of the Marcellus shale, but of shales higher up. And if it was from shales higher up, then how could it be the fracking that made the gas get into the well? It must be something about where the well passes through those shallower layers of rock. And somehow gas is getting through into the well and then going up the many sort of layers inside the well. So is that a bit clearer? Oh, I see.
Do you mean the water wells and not the fracking wells?
No, this is the fracking wells. So these horizontal fracking wells, they go down vertically and then they go horizontally. And, where they pass through these shallower layers, there must be some leakage. Because the methane isn't the right stuff for it to be Marcellus methane. And that's quite an old paper, and that might have changed, but that's my view at the moment. It seems to be coming from the high up parts, and it's in the fracking well. And I guess now I understand what you're saying. So how has it got from there to the water wells? Well, it's probably just got through the rocks. It's gone through these permeable rocks, these aquifers, and it's got into the water wells. I mean, there's really no doubt that's happened. But the point is, it seems not to be to do with fracking. It seems to be to do with the wells not being constructed properly.
If we can, in the black jacket.
Thanks very much. Just a simple question. How much greater is methane as a greenhouse gas than carbon dioxide? And what other gases emerge from fracking wells?
I'm not absolutely sure. I think it's about 30 or 40 times. Somebody might know better than me.
The global warming protects.
Yes.
Short term is 85 times.
Yes.
In 20 years.
50 years it's low.
100 years is about 35.
Yeah. So it's a lot. And the second question, do other gases come out? Yes. And that's very interesting. So again, the economists in the audience will be interested in this because shale gas wells, quite a lot of them, produce a lot of ethane rather than methane. And ethane's really a useful gas because it feeds into the ethylene, PVC sort of economy. So in the United States, lots of big refineries now process ethane from shale gas wells because essentially they're selling something much more valuable. So ethane that comes out of shale gas is much more valuable than methane because it's a feedstock rather than a fuel. I'm not sure. Potentially other gases come out as well, but I'm not a geochemist, so I couldn't tell you.
Anything over here?
So you said that it was probably the drilling of the wells, not the fracking itself, that the gas is escaping from. So are there any? Do you know of any papers which look at whether conventional wells release or contaminate the water in the same way?
Yeah, they do, and it's a shocking level, in fact. So there's been pretty big studies been done in Canada, for example. There's a paper by Bachu et al., which looks at a very large study of Canadian Albertan wells, and a lot of them are leaking. It's not just shale; it's any kind of water, any kind of shale gas, any kind of well. It's about not properly filling the well, finishing it properly, leaving it. It's probably regulation, and people not being tough on regulation. I'm probably going to get emails from Alberta now.
Hi, thank you very much for your talk and your clarity. Sorry if I'm a little bit late, I might have missed this. I'm interested in the amount of energy that's used to extract the gas. So I'm interested in the amount of energy that's used to get all the equipment to the site, the amount of energy that's used to power the drilling process. Then presumably there's more diesel to get, gas to somewhere, and then the fluids to somewhere else, and then into my house. And it strikes me that that's not particularly climate friendly.
Yeah.
And it concerns me that there are more effective ways of producing energy that don't cost the climate so much.
Yeah. So, and it's very energy intensive, because those big pumps, maybe you missed the photographs, but these enormous pumps that sit on the back of these trucks, and these produce thousands of horsepower, and there's an enormous amount of noise, lots of diesel being burnt. So, it is a very intensive process, but in the end, they obviously produce more energy or more value than they use in producing it, in the production. Otherwise, they wouldn't do it. But the whole point I think you're making is about the full life cycle, and how does that stack up with other sorts of energy? If you add in all the diesel and the energy that you need, how does it stack up with other energy types? And there was some work done by, there's been quite a lot of work done on this sort of whole life cycle CO2 emissions, or emissions generally. And for example, it was found that if you compared British shale gas produced here against, let's say, LNG produced in Qatar and brought to Britain, then the LNG from Qatar is more carbon intensive than the British shale gas. That's been a suggestion made by a couple of scientists, and it's very difficult to understand, life cycles, and that's evolving. But essentially, that was one idea. But clearly, you're right. I mean, shale gas, burning shale gas is a fossil fuel. I mean, we shouldn't be burning fossil fuels in enormous amounts.
What about the conventional gas from Norway, and how many horsepower is used?
I don't know, but I imagine it's probably a lot less. There may be people that know this better than I do. Because you're not fracking, because you're not... Yeah, you're drilling, Yeah, I don't know. But you're right, there's no doubt.
Could I ask a slightly different question? You're trying to address this quite sort of emotional question through science, and there are a number of people here who clearly sort of, have brought things into the room, and the science may interest them or not. The question is, how can you, with a series of studies, each one of which you can puncture by saying there are idiosyncratic factors at work, it was the way that well was not cemented properly, or it was the structure of the rock in Pennsylvania, or it was this idiosyncratic thing about that aquifer, and so on. Can you imagine how, through experimental fracking, you could build a body of evidence that would actually produce a sufficient level of scientific certainty for what is obviously a very important issue? How could you do that?
I think what you're kind of asking about is the process of science, and it's an endeavour which sort of self-corrects. You know, you approach a problem from many different directions. It's a very democratic activity in the sense that you've seen in America the number of papers published on fracking has gone up like that because you have many groups seeing this is an important problem, seeing that their citations are going to go up and everything else, and doing lots of interesting work. And I think, you know, what I showed you is that no one paper often clinches it. It's just a body of papers and a body of evidence which, if it's all gone through the peer review process, if it's sufficiently persuasive, that you end up with an answer, yes, it's okay to do fracking, or no, it's not okay. And, you know, it's the same with mobile phones, you know, or flying in aeroplanes, or building bridges. You know, people do things and they experiment and they do science in order to find out if they work or not. And you don't immediately solve the problem straight away. But to answer your other question, which I think is very interesting, would it be a good idea to concentrate the work in a particular place? So have a site where you test hydraulic fracturing, for example, and that is being done. So in the United States, there are centres where hydraulic fracturing, you know, is being tested under sort of conditions where you can throw lots of science at it. So I think it's a problem which, you know, is close to being solved. But in a sense, you have to get this in proportion. Thousands of wells are fracked in the United States. I can't remember the figure, something like 20,000 wells are fracked every year in the United States. I mean, there are problems, clearly, but they're not that great.
Okay, I think we have one more question in the back there. I'm just trying to give everybody a chance. And that's unfortunately going to be the last one we can take because we're getting near time.
Hello. Firstly, I'd like to take your opinion. Do you think the media and some of the environmental activists have gone overboard with fracking fear, and they've caused a chaos in the UK? And secondly, the distance between the groundwater and shale deposits. Do you think that the distance, I believe it's 100 meters or so, do you think it plays an important role in order to determine that contamination can occur or cannot occur?
Okay. First question, yeah, the media love a fight, you know. What you tend to find is that the media, I hope there's no reporters here, but what they tend to do is they like to put a pro-fracker against an anti-fracker. And, you know, it's a bit like Parliament, you know, it's all bun fights and stuff like that. It's very hard to get a kind of reasonable discussion because the media tends to prefer people expressing strong opinions, and, you know, some boring bloke like me who tries to stay in the middle, I'm not interested, you know, not that I want to, you know, be on the telly or the radio, but essentially I think that's one of the problems. Also, it's interesting that when scientists are in doubt, which is often, I mean, that's what scientists, that's the world they live in mostly, what reporters will, what people will tend to do is look at it and say, well, if you don't understand, you know, what are we to think? But in fact, uncertainty is just part of the scientific process, and you work at it and you resolve it. And those are two things that the media tend to do. But again, the media do put out important things, and, you know, that's their job to make sure that we all know if there are problems. The second question about the distance between is really important. And your 100 meters isn't right, because it really depends. It's a completely natural system. So there are places where aquifers in the UK, rocks that produce water that we can use, are hundreds or even thousands or even kilometers from shale layers. And there are places where they're right up against each other. And, you know, it's obvious that you wouldn't touch the shale that's right underneath an aquifer. There are one or two examples of spectacular problems in the United States, in Wyoming, for example, where problems have occurred. I don't think this was peer-reviewed, but there was a report published, was because they fracked layers very close to an aquifer, just underneath one, and hey presto, they got contaminated aquifer. So it is important.
Okay, well, that brings us to time. Really great Q&A and a fantastic talk. I certainly learned a lot myself, and I hope you guys all did as well. But if we can have one more round of applause for